First, we took the force sensor and we pushed the ball down into the spring cannon to record how much force the spring exerted on the ball. We then launched the ball and found the height at the top of the parabola. We at first had been recording the times, but we realized that we didn't need any time for the force of friction of air because we never could find a value of the ball in a vacuum. Once we had recorded the height, we also recorded the mass of the ball and used the force that we'd found using the force sensor to find the value of our spring.
Alright, so for our launch, what we started out with is you push the ball down in the launcher and then pull it out and it launches up. So we measured the distance that we had to push it down as 0.0389 meters, and we used a force sensor to calculate the maximum amount of force you need to apply to get the spring to move that far down, and we calculated that out to be 48.27 newtons. So with that information we can find a K value for our spring. So to find K, we know that because of units, K equals F over X, F over distance. So with that we can say 48.27 newtons divided by 0.0389 meters is going to equal our K value of 1240.87 newtons per meter. And we measure the mass of our ball to be 0.01 kilograms. So we go over here to our values of just leaving the launcher. So we have the work done by non-conservative forces equals our change in energy, which is 0, which is going to be our initial potential energy due to the spring minus our final kinetic energy. So we can say that our kinetic energy equals our initial potential spring energy, and we can plug in from that 1/2 mv squared equals 1/2 kx squared. We have all values for all of these except for v, so when we solve for v we get v equals 13.7 meters per second. So we can go over here to post-launch, where we get work done by the non-conservative forces equals our change in energy, which is going to equal our energy loss due to air friction, which is what we're solving for, which is going to equal our initial kinetic energy minus our final potential gravitational energy. So we get that equals our air friction value equals 1/2 mv squared minus mgh. And we calculated out that h equals 0.975 meters. So we get our air friction losses equals 1/2 times 0.01 kilograms times 13.7 meters per second squared minus 0.01 kilograms times 9.81 meters per second squared times 0.975 meters. And then when we plug all those numbers in, we get our energy loss due to air friction equals 0.843 joules.
Okay, so for our results, if we calculate the height without the energy lost from air friction, we'll find that the theoretical height without air friction would have been 9.57 meters. But in real life, with the loss of energy from air friction, the height is 0.975 meters.